In this video, we are going to take a look at an optimization example. Window World Incorporated is responsible for designing new windows for the expansion of the campus chapel. The current design is shown in the figure, and the metal trim used to secure the perimeter of the frame is 172 inches long. If the maximum window area is desired to let in the most light, what will be the dimensions of the rectangular portion of each window and the total area of each window? So this is an optimization problem because we are trying to find the maximum window area. So our goal essentially is to maximize area. And I always have my students write down the goal first. So the goal is going to be max area. And the reason why I like us to focus on the goal is because this is the first equation I like to try to write. If we're wanting to maximize area, then we should write an area equation first. So when I look at this figure, this geometric figure is actually made up of two geometric shapes. We have a rectangle on the bottom and a triangle on the top. So we're looking for the maximum area of both of these shapes combined. So I'm going to use A for area, and I'm going to kind of write this as my total area. So the total area of the entire window will be found by basically adding the area of the rectangle to the area of the triangle. That'll give us the area of the entire window, the entire shape. So this diagram is actually already labeled for us, so we're not going to have to choose any variable names. So if we begin with the rectangular portion here of the window, the area of a rectangle is length times width, or base times height. And in this case, the width and the length are labeled W and L. So the area of the rectangular portion will just be L times W, length times width. Now we will add that to the area of the triangle. Now remember, the area formula for a triangle typically is written 1/2 base times height. So when I'm looking at my triangle here, the triangular portion of the window, the base here of this triangle is equivalent to the width of our rectangle. So the base of this triangle is actually W. And then the height of the triangle was already labeled here as H equals 0.866 W. So when we do our area formula, 1/2 base times height, the base is W, and then the height is going to be 0.866 W. So if I go ahead and multiply and simplify, we have L times W plus, I'll multiply 1/2 times 0.866, and that will be 0.433 W squared. So right now, this is my area formula for the area of the entire window. Now, as I look at this area formula, I notice that this is area, and it is as a function of length as well as width. So this is not the area in terms of a single variable, but rather there are two variables here. And that's a problem. I can't find the maximum unless I have just one input and one output. So next, I need to basically look for another relationship between my variables. This second equation, or this second relationship between the quantities, is what I often call the constraint. So I like to label this as my constraint equation. So as I reread the problem, I notice that it mentions the metal trim that's used to secure the perimeter of the frame needs to be 172 inches long. So that's an extra piece of information that I haven't used yet, and this is like a limitation, or what I'm calling a constraint. We need to have the outside perimeter of the window be equal to 172. So essentially, they've told us that the perimeter must equal 172 inches. So let's see if we can write an expression for the perimeter. Remember, the perimeter is the distance around. So we have the width on the bottom here, then we have the length, then we have these two triangular sides, and then on this side here, remember this value here, the left-hand side, since it's a rectangle, would also be labeled as L because the opposite sides of a rectangle are going to be the same length. So if we were to add all of these together, we essentially would have 3W plus 2L, and that would be my expression for the perimeter, and the perimeter must equal 172 inches. So my constraint equation is 3W plus 2L is equal to 172. Now let me just mention we're not using the h equals 0.866w because remember that's the height of this triangle, but that is not the distance around the entire window. So if I were to just highlight again to be very careful, when we're doing perimeter, we want to make sure we're just going around the outside, okay, the outsides of the shape. So now the use of this constraint equation is it's going to allow us to basically substitute into my area model here and eliminate a variable. So in the constraint equation, we can either solve for W or we can solve for L. It doesn't make any difference which one you choose. You can just pick one, pick whichever one seems to be easiest to you. I'm going to go ahead and solve for L. So I'm going to subtract the 3W. So I'll have 172 minus 3W. And then I'll divide by 2. And remember, when you're dividing by 2, you want to divide all of the terms on the right-hand side by 2. So we have 172 divided by 2, which will be 86, minus 3 halves W. And I like to go ahead and put a box around this equation because that gives me a nice relationship between length and width that may be useful later on. And I'm going to now substitute that constraint equation into my area model, and that will eliminate the variable L and leave me with an equation that is entirely in terms of W. So 86 minus 3 halves W times W plus 0.433 W squared is my model. I do want to go ahead and simplify, so let's distribute. We'll distribute the W. So our area is equal to 86W. Now, since the 0.433 here, since that's in decimal form, I'm going to go ahead and convert 3 halves into decimal form as well. I would only do this in this case because 3 halves works out to be exactly 1.5. If it wasn't an exact decimal, then I would not convert it because I don't want to round. But in this case, it is. So I have 86W minus 1.5W squared plus 0.433W squared. And I can go ahead and combine like terms. I'm also going to list the W squared term first. So that will leave me with a negative 1.067 W squared plus 86W. And this is my area model, and you'll notice it is entirely in terms of W, so it's in terms of a single variable, which is exactly what we wanted. I'm going to actually go one step further, and I'm going to write this in function notation using area as a function of width, so that's A of W. And this is what we would call our mathematical model. We just created an area model, and this area model relates the width of the window to the area. So now going back to our goal is to find the maximum. And we could pause here and go to our graphing calculator. We could graph this curve and use the calculator to calculate the maximum. But we have a little more knowledge that we can use rather than running to technology right away, because we should recognize the shape of this area model. So because this model is degree 2, we know this is a quadratic function, and the graph of a quadratic function is going to be a parabola. Now notice, in addition to that, the leading coefficient is negative, so that's going to cause the parabola to open down. So if I just visualize, without using any technology, visualize a parabola that opens down, we know that we are going to have a nice clear maximum here at the vertex. So the maximum will occur at the vertex in this case. So really, finding the maximum just requires us to locate the vertex of the parabola. I am going to go ahead and mention when I label the coordinate of the vertex, typically we say our coordinates are always x comma y. But in this case, looking at our area model, the input variable is actually w, width, and then my output is a, area. So when I calculate the vertex, I'll be calculating the width, which is the x value, and the area, which is the y value. And we have a nice vertex formula to do that. So the vertex of any parabola or any quadratic function can be found by using the vertex formula, the opposite of b over 2a. Now remember, that's finding the x value of the vertex, and in this case, the x value is w, it's the width. So negative b over 2a. b is 86, so that'll be negative 86 divided by 2 times the a value, which is the leading coefficient, of negative 1.067. So negative 86 divided by this quantity. You can go to your calculator for that. And I should mention, be sure that you're pausing the video and grabbing your calculator so that you are checking your calculator skills at the same time. So this looks to give us approximately 40.3. It's really 40.2999, but because of all of those nines, I'll go ahead and round this to just 40.3. Now, because this was the width, and if I go back to the perimeter, which was measured to be 172 inches, then this would be 40.3 inches if we have our correct label. So part A of this problem, scrolling back up, part A asked us to find the dimensions of the rectangular portion of the window. So the rectangular portion had dimensions W and L. So we have essentially found W, and now we need to find L. So we have one of our dimensions here, 40.3 inches. That's our width. But now we need to find our length. So if you go back and look at the two equations that I have boxed in, let's take a look at them. I have my area model here, the area in terms of the width. So if I substitute W into this equation, my output will represent the area of the window. And then I also have my constraint equation over here. If I substitute W into this constraint equation, my output will be L, the length. So that's where I need to substitute in order to find the length of the rectangle. So my length is 86 minus 3/2 times W, and W is 40.3 inches. So that works out to be 25.55. And that is the length, so that would also have a measurement of inches. So we have our width and we have our length. So right now we have our complete answer for part A. So part A, which asks for the dimensions of the rectangular portion of the window, will be 40.3 inches by 25.55 inches. Those will be the dimensions of the rectangular portion of the window. So now moving on to part B asks for the maximum area of the entire window. So this is where we actually want to find area this time. So we can take that width, W, which is equal to 40.3, and substitute it into our area model, and that output will give us our area. So we will basically be finding A of 40.3. This is essentially the Y value of the maximum, which is at that vertex. So A of 40.3 will be negative 1.067 times 40.3 squared plus 86 times 40.3. And again, going to our calculator with this gives us 1,732.89597. So I am going to just round that. If I go to the nearest hundredth, actually, that'll be 1,732.9. So this will be the maximum area. And if the dimensions are in inches, then we can say that the maximum area which is the maximum amount of light that can come through this window, is 1,732.9 square inches. So this would be our answer for part B.